Welcome back to the last section of chapter 2. This section we're going to be solving inequalities in one variable. So we've solved inequalities before. We've solved things in one variable before. We're just combining them. This is going to use uh, a lot of those same skills. We're going to be factoring polynomials. We're going to be looking at graphs. We're going to be using quadratic formula, things like that. We're going to be dealing with rational functions. And we're just going to be doing them with inequalities. So our learning targets determine values that will cause a polynomial function to be zero, positive, or negative. Solve polynomial inequalities. Find values causing a rational or radical function to be zero, undefined, positive, or negative. Solve rational, radical, and absolute value inequalities. And then solve applications involving polynomials and rational inequalities. So those are the same thing that we've been working on, only they're inequalities now. Notice that these two are basically the same, only polynomial as opposed to rational or radical. These are basically the same, except polynomial, rational, radical, absolute value. And honestly, absolute value is actually the exact same as way you do it with a polynomial. So let's take a look at some polynomial inequalities. Before we get to inequalities, let's take just a look at a polynomial function and see what's going on here. So we have this function, it's factored for us. We can factor those, it's factored. We have zeros at x equals -3, and we have a double root at x equals 4. Notice this one right here gives us a complex root, which is great when we're finding zeros, but that's not going to change the sign. And we're going to be looking at what sign is the polynomial going to be on these intervals. So if we were to graph it like that x squared plus 1, like it would give us a curve, but it would be like up there. It's not going to come down and cross the axis. This is upside down from what it will be. But the only time it's changing from positive to negative or vice versa will be at the actual zeros, the real zeros. So we know that that's when it's going to be 0. We can make a number line here. 0, -3, and +4. So it's going to be, I should have labeled 0 down here. So it's going to be 0 at these values. Those are the roots. That's what we've been finding this entire chapter, basically. Now, we're not concerned so much with those. I mean, those are important. We're concerned with what's happening in between there and on the outside. So all we need to do is we need to just plug in a value. We could plug in 0 to figure out what's going to happen in between these two values. Is it going to be positive or is it going to be negative? It's going to be one or the other, and it's not going to change, because in order to change, it would have to go through 0. So if we plug in 0, we have 0 plus 3, well, that's positive. This middle one's always going to be positive, because x squared is positive plus 1 is positive. So 0 plus 3 is positive, that's positive. 0 minus 4 is negative. 4 squared is positive. So the stuff in between -3 and 4 is going to be positive. Then we need to pick something less than -3. We could plug in -5. If we plug in -5, x minus 3 will be a negative, because -5 plus 3 is a negative. -5 squared plus 1, that's always going to be a positive. -5 minus 4 is going to be a negative, but we're squaring that, so that'll be a positive eventually. So we have a positive times a negative. That'll give us a negative value. Notice I didn't actually care what the value is. Like, what the value is doesn't matter so much. What we're looking for is it going to be positive or is it going to be negative? And then something on the other side of 4. Something on the other side of 4 could be, say, 10. If we plug in 10 plus 3, we get a positive value. 10 squared plus 1 is a positive value. 10 minus 4 is a positive value squared. So a positive times a positive times a positive squared is going to be a positive value. So if we were to graph this, we would have at -3, we'd have at +4, we'd have a graph that was negative, then positive, then it came down, it hit 0, and went positive again. And you might be looking at that thinking like, wait, that's an odd function, and we have 4 factors up here. But remember that x squared plus 1 is actually 2 factors, so this is a 5th degree polynomial. Now, what exactly happens in between the roots? We don't know. There's going to be some funky jazz going on right there because of that x squared plus 1, or it'll be going on over here. But either way, it's going to stay positive. Why is this important? This is important because our questions are not going to be f of x equals blah, 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 blah. It's going to be when is f of x greater than 0? Well, it's greater than 0 between -3 and 4, and from 4 on. So from -3 to 4, and then the union connects it, means and, or 4 to infinity. That's when it's greater than 0. When is f of x greater than or equal to 0? Well, now we can include the -3, and we can also include the 4, which means we don't need to split it up any. So from -3 to infinity. When is f of x less than 0? Well, it's less than 0 before -3, so from -infinity to -3, and that's it. And then if it was less than or equal to 0, we'd go from -infinity to -3, but we could include the -3, so we can have the square bracket. And so the questions there, it's going to be like, it's going to ask one of those questions. And so we need to figure out where it equals 0, figure out what it's doing in each of those little intervals, and then we can answer the question. It may give multiple questions, like I just did. It may have you find where is it increase, or where is it positive, where is it negative, and that would be with a function like this. Usually, though, we'll have an inequality. Looks kind of like this. So, first step, we need to factor this. So to factor this, we can look at, we have our coefficients of this divided by our coefficients of that. And so 24 has a lot of different coefficients that it could possibly be. So that does not narrow it down a whole lot, but it doesn't narrow it down a whole lot. But we could, look at a graph. We can see it's like, hey, let's start with 4 in this case. I don't have a graph coming up here, but we could start with 4. Then 2, -7, -10, 24. So bring it down, multiply, add, multiply, add, multiply, add. So 4 is one of our roots. So this gives us x minus 4 times 2x squared plus x minus 6. Has to be greater than 0. Now we could try to factor this other one. So we have x minus 4 times 2x and x. So let's see, two things that multiply to give us -6 would be a 2 and a 3. Let's go a +2 and a -3, so they multiply to give us -6. 2x times 2 is 4x, and then minus the 3x gives us 1x. So that has to be greater than 0. So our zeros now, we have x equals 4, 3/2, and -2. So we're going to have -2, 3/2, and 4. We need to plug in some values and see what happens here. And we plug them into the factored form. So if we choose something very negative, say -10, -10 minus 4, that's going to be a negative. And then times the middle one is going to be a negative. And then times -10 plus 2 is going to be a negative. A negative times a negative times a negative is a negative. Plug in something in the middle, like 0. Well, 0 is -4, -3, and then +2. So a negative times a negative times a positive will be a positive number. Plug in something between 3/2 and 2 and 4. 2 or 3 would be my recommendation there. Well, either of them -4 is going to be negative. Multiply by 2 minus 3 is going to be a positive value. And then that number plus 2 will be a positive. So a negative times a positive is a negative. Then plug in a big number. We're going to get a positive times a positive times a positive, which is a positive. So now we know where it's positive, where it's negative. We are looking for it to be greater than 0. That's where it's going to be positive. That's here, and that's here. So our answer would be from -2 to 3/2, or from 4 to infinity. There we go. If it was less than 0, it would be the negative ones. If it was an or equal to, we'd have the square brackets on things. Never on the infinities, though. Infinities always have the curved parentheses. So that's how we deal with the polynomial inequalities. It's the same stuff we've been doing. We still have to factor, we still have to do synthetic division, we still have to do all that stuff. It's just now we're not necessarily looking for just what are the zeros, we're looking for what's going on in between the zeros. Another one, we can move this over, so we have x cubed minus 6x squared plus 8x minus 2 is less than or equal to 0. Now, if we tried to factor this, it's not going to be pleasant because this one, turns out, does not have any rational roots to it. So what's another option? We can graph these things. So if we graph it, we get this. Now we're looking for when is it less than or equal to 0. So we want that interval and that interval. But where are those values? In this case, I graphed this using Desmos because I'm figuring out how to use that, and it's really nice. If you click on it and you click on the intercepts, it will tell you what those points are. You don't even need to do the find intercept thing. So we want down here and in between. What it doesn't do is it won't let you like copy the picture with the points on it. The points disappear when you try and do that. So I had to get around that. So we are going from -infinity to 0.325 roughly. Then it's an or equal to, so we get square union, and then from 1.461 to 4.214. So we can graph it. We can see that, hey, look, it's negative here. It's positive in the other places. And so we want to choose the times when it's negative. But there we got it. We said it equal to 0. It's not technically equal, it's less than or equal to 0, but we got everything on one side so that 0 was alone, and then we graphed it, and then we just had to look to see where our intercepts are. Rational inequalities. So rational inequalities are going to be basically the same. We're going to start with a function so we can see what's going on. So they will cross the x-axis when it equals 0. That's when the numerator equals 0. So we'll have zeros when x equals, well, 2x plus 1 equals 0, so negative 1/2. But it can also change signs at a discontinuity. What kind of discontinuities do we have in rational functions? We have vertical asymptotes. So vertical asymptotes are also going to be some of these values. We could call them critical values if you want. Vertical asymptotes at x equals -3 and 1. And so those are the values we're going to need to look at. -3, -1/2, and 1. And we need to see what's going on in each of those regions, because as we graph this one, we would get something that looks like we have a vertical asymptote there. We have -1/2. It's going to hit a 0 there. We've got a vertical asymptote here. We'll graph it once we figure out the values here. So if we plug in a number less than -3, like say -5, the top -10 plus 1, that's going to be a negative, over -5 plus 3 is a negative, -5 minus 1 is a negative. So we have a negative divided by a negative times a negative. This is going to be a negative value. Let's see, our x-intercept, or our horizontal asymptote 0, so this is going to be like that. Between -3 and -1/2, say -1. -1 times 2 is -2 plus 1 is going to be a negative. -1 plus 3 is a positive. -1 minus 1 is a negative. So we have a negative divided by a positive times a negative. That's going to be a positive value. So just like when we were graphing our rationals, I used the wrong color there, but that's okay. Plug in a number in between there, like 0. So 0 plus 1 is 1, that's a positive. Over 0 plus 3 is a positive. 0 minus 1 is a negative. So a positive divided by a positive times a negative is a negative. So that's going to go down to the asymptote that way. And then plug in a number bigger than 1. When we plug in a number bigger than 1, we're going to have, well, a positive and then over a positive times a positive. And so that's all going to be very positive. And so it's going to come from the positive and to our horizontal asymptote of 0. So notice here that it changes when it hits 0 and at those asymptotes. So if we were looking for r of x to be greater than 0, well that, oh, I color coded it, that's the red stuff. It'll be from -3 to 1/2, -1/2, and then from 1 to infinity. If we wanted r of x to be greater than or equal to 0, we're still going from -3 to -1/2, but it could actually equal 1/2, and then from 1 to infinity. So again, the infinity is parentheses, not a square bracket. The asymptotes are also parentheses because it cannot equal the asymptote. So that -3 and that 1 stayed asymptotes. If we wanted where it was less than 0, it would be the same thing, but we would have the blue ones. So it would be from -infinity to -3, and then from -1/2 to 1. So we can look at one. We have something like this, 5 over x plus 3 plus 3 over x minus 1. We can multiply, like get our common denominators. So this one we'd want x minus 1, x minus 1. This one x plus 3, x plus 3. So 5x, or x minus 1 times 5 will be 5x minus 5, plus 3 times x plus 3 is 3x plus 9, over x plus 3 times x minus 1 is less than 0. We can combine 5x plus 3x is going to be 8x. Negative 5 plus 9 is plus 4 over x plus 3, x minus 1 is less than 0. We need to find our zeros. Zeros when 8x plus 4 equals 0. So subtract the 4, divide by 8, x equals -1/2. The vertical asymptotes are going to be at -3 and 1. Again, this is basically the same one that we just did. Actually, it is. In fact, if we went 2 times, 4 times 2x plus 1, now it is the same one that we just did. So that 4 is not going to change the, it's not going to change the values at all as far as positive and negative goes. So when we start plugging stuff in again, we're still going to get that it was negative over here, it was positive there, and it's negative, then it's positive. Now we're looking for it to be less than 0, so we want the negative. So we want that piece and we want that piece. So our answer here would be when it's less than -3, so that would be -infinity to -3, or when it's between -1/2 and 1, so -1/2 and 1. That's when that's when that rational inequality is less than 0. So again, make it a one fraction and solve it. You could have actually solved by multiplying both things by the common denominator as well, but that just gets a little bit weirder because it's nice to see the vertical asymptotes there. Otherwise, weird stuff happens. So I would recommend writing it as a rational function and then dealing with it that way. Other inequalities. So we could have things like a square root. We could have absolute values. Absolute values are going to be the same that we just did. They could be in polynomials or in rational functions. You do it the same. You treat it just like a root or an asymptote, but it'll always be positive. It will never contribute a negative to your value when you're looking at the signs. Here, we have a 0 at x equals 3 from that guy. From this, that's not going to give us a 0, but x has to be greater than or equal to -1. We have a domain restriction. So on our number line, we can actually start it at -1. Nothing before that's going to matter because it's going to give us something that we can't even deal with. And then 3, we just need to plug in values. We could plug in 0. If we plug in 0, we're going to have a negative times a positive. The square root will always be positive, and so this will be a negative. And then if we plug in a number bigger than 3, say 5, we'll have a positive times a positive, which will be a positive. So we're looking for when is it greater than or equal to 0? It's greater than or equal to 0 in that place. So 3 to infinity. If you tried squaring this or something like that to get rid of the square root, you'd end up with a plus or minus 3, but we can't deal with negatives anyway, so we get that. So this is looking at inequalities. Again, it's doing the same stuff. You can always use a graph to help you visualize what's going on, whether it's polynomial, rational, radical, whatever. Don't be afraid to graph it. Um, and then look to see, is it greater than or less than 0? When it's an or equal to, don't forget to make it a square bracket for those zeros, but never a square bracket for asymptotes or infinity. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.